Hello friends, this is Sushrut Tendulkar and welcome to my YouTube channel. This is the first tutorial in the series ML Chronicles. In this tutorial, we're going to learn how to build a simple logistic regression from scratch. Let's get started. Alright, in this tutorial, we're going to cover these different aspects. So we'll first look into the dataset, the kind of dataset we'll be using for this tutorial. We'll understand the process at a high level. We'll then look into the different functions that are used while training the dataset. We'll look into the complete code, and then finally we will evaluate our custom built logistic regression model along with the one that is provided by sklearn. To begin with, so there are two aspects to building an algorithm. How will the algorithm behave during the training time and how will it behave during the test time? During the training time, we will first assign the random weights to the weight matrix. We multiply the weight matrix by the input values. Then we use sigmoid function to squash the values between 0 and 1. That's the nature of logistic function. Then we compare predicted output with the actual output. Then use that information to backpropagate and update these weights. And then you do this process multiple times until you get the optimal value. This is what will happen during train time. And during the test time, we'll use these same weight matrix and we multiply that with the new unknown value and then use sigmoid function to squash the value between 0 and 1, and that will be our prediction. Let's start with understanding the dataset. Let's import all the necessary libraries, and we'll be using a sklearn dataset to import the breast cancer dataset, and we can load this using this simple function call, and we'll store them in x and y variables. That is done. Now let's do a simple visualization of this dataset. PD is not defined. Okay, let's define PD as well. Okay, we need MP as well. Yes. So we have around 31 columns. Last column is for the target variable, and there are basically 30 different features in this dataset, and there are around 569 samples. So 569 samples and 30 different features. And one thing we can quickly notice here is that the features are at different scale. So this is in 17, 10, 122, this is 0.1 and all different scales. So we use min-max scaler to align them into a proper scale. So we have stored all the data in x scaled value. Now what are we doing here is this. Can we see this? Okay. So we have around 569 training examples with 30 different features. We want to find an optimal weight matrix that when multiplied with input values will give the expected output values. Here, irrespective of number of input training examples, this weight matrix depends on the number of features. So there will be one weight corresponding to individual features here. And when we multiply this with weights, for example 569 by 30 multiplied by 30 by 1 will give us a vector of 569 by 1, and that will be our y hat or the prediction. So this is what we're going to do during the training time and mostly during the test time as well, and we'll see how will we do that. Now let's define different training functions that are needed here. First, calculating z. What is z? So Z is nothing but the term. We get Z by multiplying the individual features with the corresponding weights. So this will be x1 into w1, x2 w2, and xn wn. I've written a blog post about this. You can go through them in detail, but I will try to cover the highlights of it here. We can imagine this implementation in terms of a simple neural network itself. So we'll have an input matrix here, then the corresponding weights, and then we'll have some function that will squash the values between 0 and 1, and then we get the output. We calculate the gradient, and then we backpropagate here and update the weights, and then we repeat this process. So as a first step, we calculate Z here. So that is multiplication of individual features with the corresponding weights. Let's see how will you do that. It will be simple matrix multiplication. We'll get some error here, that's totally fine. So we haven't defined weights yet. This is for our understanding. Just saying that we're going to multiply all the input vectors with the corresponding weights, and we'll store that value in Z. So we'll define weights in next steps, but this is how we calculate Z. Next, what we want is a sigmoid function. A sigmoid function is something that will squash the value between 0 and 1, as we said before. So the function will be 1 by 1 plus e to the power minus z. And why this will be the activation function for logistic regression is something that we'll cover in a separate tutorial. But for now, let's assume that this is the logistic function that we're going to use. But there is a derivation as to how this is the actual function that we're going to use for logistic regression. But for now, let's assume that this is the one. Again, corresponding function, we will define it here. It will be, we pass any value and then it will calculate 1 by 1 plus e to the power minus z. And we can pass any value, but ideally the returning value from this function will be between 0 and 1. Right? Even if I pass very high value, the value will be still, it's very close to 1 here. Okay, already we have calculated z and then the sigmoid, and then what we need is the loss function. Now, what is a loss function? So loss function is something that will calculate if the calculated value and the predicted value are same. So that's how we can define loss function as. And this is the loss function for the logistic regression. And why this should be the logistic function, or sorry, why this should be the loss function is something that I will cover in a separate tutorial. So what does it say is that while training, if the actual value is 1, then our loss function will become minus log of y hat. Y hat is something that we have calculated here using sigmoid. And if during training the actual value is 0, then we calculate loss function as negative log of 1 minus y hat. This is the loss function, and this can be combined into one single function like this, and it's simple representation of writing if-else function. So if we were to write this in if-else format in any coding language, this is how it would be. We are multiplying y into log y hat, plus 1 minus y into log of 1 minus y hat. So if y is equal to 1, this term will be kept and this one will become 0, because y will be 0, 1 here, 1 minus 1 will be 0, and this term becomes 0, and we'll be left with only this. And if y is 0, this term will become 0, because 0 into this will be 0, and 1 minus 0, and only this term will be retained. So basically this is written in this particular format, and then we divide by the number of training examples here to normalize it. So how will we do that? So we'll define a simple loss function. All we need is x and y and the weights. So first we'll calculate length of x. This is the number of training examples. We'll calculate z. We'll calculate y hat using sigmoid, and then predict 1. Predict 1 is this part here, and then predict 0 is 1 minus y into np log of 1 minus y hat, that is this part here, and then we return the negative sum of these products here. So basically this summation multiplied by 1 by m. So this will be the loss function that we'll be using for logistic regression. Again, as I said, why this should be the loss function for the logistic regression is something that I will cover in a separate tutorial. Now, next what we want is gradient descent and derivatives. So now we know that loss function. What we want is we use this output of loss function to calculate gradient, and hence we'll use this for updating the weights, because that's the ultimate aim that we want to achieve here. So we want to have a perfect weight so that that can be used for prediction. So how do we do that? Gradient descent and derivatives. Now we want to calculate the derivatives of loss function with respect to the weights here, W1, W2, W3. But note one thing here. Z is calculated from W1 or weights W. W is a vector. And Y hat is calculated from Z. And L is calculated from Y hat. So we want to calculate dl by dw, that is loss with respect to weight, but you can't directly do it here because the w term is directly not available in the loss function. So that will lead us to use the product rule of calculus, that is dl by dw can be written as dl by dw equals dl by dy hat into dy hat divided by dz into dz divided by dw1, because it's not directly computed here. So that's what we are saying it here. dl will be dl by dy hat, dy hat by dz, and dz by dw. So now let's calculate each of these separately. So let's calculate dl by dy hat. Looking at this function, let me zoom it a little bit. Yeah, so we have our loss function here. We will have to calculate derivative with respect to y hat. Now there is y hat here, then there is y hat here. So if we look into this term, I is a constant and derivative of log x will be 1 by x. So this term will become yi by y hat, right, because of log function here. Similarly this one, 1 minus yi divided by 1 minus y hat into derivative of this, that will be minus 1. So that's how we'll calculate dl by dy hat, right? So negative y log y hat, so why this minus sign is because of this. So minus of this in plus or minus of this term. So this will be minus by y hat, and this will be minus y into log of 1 minus y hat. So that will be nothing but 1 minus y by 1 minus y hat. So we got the derivative for this. Next let's calculate dy hat by dz. So we have y hat function here, that is 1 by 1 minus e to the power minus z. Now this can be brought to the numerator, so then that will become 1 plus e power minus z to the power minus 1. And we know that x to the power m can be calculated as m into x to the power m minus 1. So we can use the same logic here, and then we can calculate the derivative for the second term. So this can be written as 1 plus e to the power minus z to the power minus 1, and then the derivative will become minus 1 into 1 plus e to the power minus z into minus 1, that will become minus 2, and then into derivative of this, the term which is inside here. So then we can simplify it further, and then ultimately it will become 1 minus y hat into y hat itself. So this will come into this particular format, 1 by 1 plus e to the power minus, it should be z here. So this is nothing but y hat itself, and this term will become 1 minus y hat. So ultimately dy by dz will become 1 minus y hat into y hat itself. So that's a very neat format to work with. And in the end we need dz by dw. So we have z term here and we want with respect to dw. Now w is a vector, it's a collection of scalars w1, w2 till wn. Now if you take dz by dw1, then the value will be x1. If you take dz by dw2, then the value will be x2, because w1 will go off and then constant will remain here. And since we want this entire thing with respect to the entire vector w, we just retain xi. Instead of saying x1, x2, x3, we just retain xi. So that's what we will do here. So z is defined as this, and for each of this, if it is as I said dz by dw1, then the constant x1 will remain, dz by w2, x2 will remain, so forth. So we'll just call it as xi. So now we got all these three terms, this and xi. So then we'll multiply all of them together, right? And this one and this term will get cancelled, and what remains is xi into y hat minus y. So this is a very clean format, and this is the gradient with respect to weight from the loss function, and this is all we need for calculating the backpropagation, right? So let's use that in the gradient descent and derivative function. So for each of the epoch, right, so what we do here is we calculate y hat minus yi into x, like how we got in this formula here, and then we use a learning rate, and then we'll update the weights here. So this is the final part of the training set. Now that we have defined all the functions that are required for calculating the training set, let's quickly see the complete code. So again, training code and testing code. Let's see the training part of it. We have defined a sigmoid function, and we have added an intercept. This is optional, and we have calculated the loss function here, and we have already defined how to calculate loss function. We are calculating the z, then the sigmoid, and then predict one term, predict zero term, and then returning the sum here. And then this is what we do within the fit function. We take x and y as inputs, epochs 25 and learning rate default value, and then if it's required we add an intercept here, and then we calculate the length. And within epoch, all we do is calculate z, calculate y hat value, and then this is the gradient part which we calculated, y hat minus y into xt, and then use the learning rate and divide by n, because we are doing it for all the 10 examples together, and then update the weights. And we are doing minus equal to here because this is gradient descent. And why it is gradient descent, again as I said, I'll cover it in a separate tutorial. There's a reason for this, why it is minus equal to and why not plus equal to. And finally we calculate the loss function separately using this function here. We needed loss function for calculating the gradient here, but we can do away the loss function. We can do away with loss function here, but we are using that to calculate the loss separately, and we want to print the loss as well. But ideally for training purpose we don't need this loss function separately calculated, but we are using it for visualization purpose. And then we store the weights and then the loss. And in the testing part we have a predict function here. We have already defined our weights, it's already stored in the self-plot weights. We multiplied that, and then we use the sigmoid function, and then whenever the value is greater than 0.5 return 1, if it is less than 0.5 return 0. So I'm going to copy this and put it into the same logistic function. Oops. Tab, and I'm going to run this. So now our this LR class is the logistic regression function that we have implemented. Now let's do the training part. So I'm going to divide the dataset into train and test dataset, and I'm going to call this LR function, LR class that we have defined, and create an instance of it, and then I call the fit function here. with 200 epochs and 0.7 as the learning rate. So let me run this. It ran and it just took 44 microseconds. It's very fast. And if I calculate the mean or the accuracy, it is 95%. It's a very good accuracy. And if I have to calculate the F1 score, so we got F1 score of 0.97 and a very good recall of 0.98. So this is the accuracy of our logistic regression function. And if we have to plot the loss that we had stored earlier, so it falls down till 25 epochs and then gradually it falls down till 200 epochs. So 200 epochs is something that you have defined here, and for each epoch we see that drastic fall in the loss. And now let's compare this with the actual sklearn implementation of logistic regression. So I'm going to call logistic regression from sklearn. I'm going to call fit and then I'm going to predict it. So it took 339 microseconds and ours took around 44 microseconds. And if I calculate accuracy, this is 98. This is slightly higher than what we got here with our model. And if I have to calculate the F1 score and everything, yeah, it's slightly better than our model. It's 0.99 and we had got around 0.97. But nonetheless, our model is comparable to the sklearn implementation. Well, in this tutorial, we had built our own custom logistic regression using the loss function and the gradient descent. We trained a breast cancer dataset and calculated accuracy and F1 score, and then we trained the same using sklearn's implementation of logistic regression, and we compared the results, and we can see that the results are almost similar. Well, that's it for this tutorial. Thank you so much for watching. Keep learning. Bye bye.